Because, do you hear me?
Yes, Ratko, we can hear you.
Thank you for your introduction, and thanks also to the organizers for inviting me to speak to this seminar. So, as the title suggests, we will be counting rational points for some algebraic stacks. We will we will see how to formulate the conjecture and to see like some case when it is true. So the example that we will spend most time with is counting of elliptic curves. We can use the following heights. Let me say, each time when I say we count elliptic curves, what I want to say is we count isomorphism classes of elliptic curves. We use the following heights, like there is a notion of naive height is defined for elliptic curves over Q. So what you can do, you can represent elliptic curve in this form, y squared is x3 plus ax plus b, where a and b are taken to be integers, and such that for every prime p, you have that either p4 does not divide a or p6 does not divide b. And once you get this equation, like you define naive height to be maximum of this absolute values of a and b when they are properly homogenized. Okay, and now we have also notion of unstable Faltings height, like which is defined for elliptic curves over a number field. This is like formula thanks to Silverman. We can represent this height as follows. Like we have this product here. Delta mean is the minimal discriminant. Tau EV is chosen in the upper half plane so that E of QV bar is precisely the quotient C by the lattice generated by 1 and tau EV. Then this is a modular discriminant. Here, this is the imaginary part, and we can see that in fact, delta times imaginary part power 6, this is a function which is invariant for SL2Z action on upper half plane. And we can in fact take any tau if you want, you can take it in the fundamental domain. And you take this product and you get Faltings height. Now this height satisfies the following property. For every b, there are only finitely many elliptic curves such that their height is less than b. In the case of naive height, it's like easy statement. For Faltings height, it's a little bit harder. Now, if you are interested in the asymptotic, like you have the following counting results. If you count elliptic curves over Q with the naive height less than b, you get the following asymptotics. This again is not too hard to prove, and much harder is counting with respect to Faltings height. We get the following asymptotics. We see the exponent of b is the same. We see that we have a zeta of 10 appearing, and of course the leading constant is different. And we would like to see this as as prediction of Manin pair for certain algebraic stacks. Now, why do we need algebraic stacks? Of course, elliptic curves are not classified by schemes. They are classified by schemes over C. But if you want to count them over Q, you need to work with stacks. We have stack M11 that we call classifying stacks elliptic curves. V morphisms from V to M11 correspond to smooth morphisms E to V, so that all geometric fibers are elliptic curves. When I'll be speaking about in stacks, I will ignore these issues that this is normally regarded as a category and not as a set. We regard it as a set simply by looking at the isomorphism classes of these morphisms. Now we have a class of stacks that we call quotient stacks. We have action of an algebraic group on a variety, and the quotient stack X over G classifies G torsors together with the G equivalent morphism from a torsor to X. Okay, and we will use the usual notation BG for the quotient stack point divided by G. Now, like the class of stacks, of the quotient stacks for which we will study Manin conjecture are called weighted projective stacks. We take A to be a positive vector with integer entries. We have action of Gm on an minus 0. Like we act to jth coordinate with the weight aj. So we have this action, and we denote it. We denote the quotient stack by P of A. Like one should like separate the notion of weighted projective space, which is GIT quotient for the same action, and weighted projective space is the quotient in the category of schemes, and this is not a scheme, this is a stack. And moreover, like this quotient is smooth, while the space is similar. Okay, and when n is equal to 1, one has that stack B mu A is like P of A. This follows like because we have normally the Kummer, like mu of A Gm to Gm 1, you have the Kummer exit sequence, and then you can see that B of the first algebraic group is the quotient of the last by the second. And this shows that B mu A is P of A. Now, let us study rational points of these stacks. Recall that by Hilbert-90 theorem, a GM torsor in et al. Or FPPF or FPQC topology is locally trivial, or trivial is a risky topology. This means that if I take a local ring and like all these cohomology groups in any of these topologies are trivial. In other words, there is every GM torsor is isomorphic to the trivial one. Now, like I said, a point of P of A like corresponds to GM apparent morphism from GM to n minus 0. And I didn't say on the last like a minute ago, I didn't say when do you see the two morphisms define the same point. Like imagine you have a morphism like this, which is GM equivariant. If you have another one, then you say that these two morphisms define the same point if there exists T such that like here T is inside of GM R, and we are here also GM R, such that like when you multiply by T and you compose by Y, you get X, or in other words, like because Y is GM equivalent, you can do that, and you can see T as morphism here, like you can get that, so firstly Y composed on T is equal to T composed on Y is equal to X. And then the condition is in fact that it turns out to be X of 1 is equal to T like multiply by Y of 1. Okay, from this, we can deduce what are points of P of A. They're precisely given by an minus 0 of R divided by the induced action of R on this set. If K is a field, of course, this is Kn minus 0. Now we can like say how stack M11 embeds into this stack P46. Like you take a representation of elliptic curve, like let's say over some local ring R, and then you map X3, this elliptic curve, you map to the point with homogeneous coordinates A and B. Of course, if you have isomorphic elliptic curve, then this will go to CD, but you know that there exists T inside of GM of R such that T4C is equal to A and T6T is equal to B. Hence, these 2 points are indeed the same point into weighted projective stack. And of course, if you want to get embedding of stacks, you need to firstly say that elliptic curve over a variety admits in the Zariski topology equations. Okay. So we have seen this stack as a substack of P46. And now, like we will define topology on PA of QP. Like firstly, recall that for every V, which is locally of finite type QP scheme, one can put like a natural topology on V of QP. And the topology further satisfies if you have a morphisms of schemes, then you get a continuous map. And if you have an open immersion, you get open immersion. If you have closed immersion, you get closed immersion. This is further compatible with fiber products. Okay, let us now define topology on this thing. So we say that the subset U of PA of QP is open if, like, for every morphism of stacks V to P of A, where V is a locally finite type QP scheme, the preimage on QP points is an open of V of QP. Like, this definition is due to Moribéry, and when, like, you can prove that the Plotchka space P of AQP is precisely the quotient space QPn minus 0 divided by QP times. Like, this is not true in general, that if you have a quotient stack x over g, that on QP points you get the quotient x of QP, g of QP, because you don't have necessarily Hilbert-90 theorem. And in fact, one can prove that if G is special group, then indeed you get that QP points of the quotient stack are precisely x of QP divided by g of QP. Okay. Let us understand the line bundles on this stack. We recall that if we have a quotient stack x over g, like a line bundle on x over g, like, is the same data as to give a line bundle on x together with the g linearization. Okay, recall the g linearization is just extension of the action of g on x to the total space of L. And in this, like, the sections, like the sections of line bundle on x over g will correspond to invariant sections on x. Now, like, if we want, in our case, x is an minus 0, and the picker group of this a minus 0 is trivial. Hence, the category of line bundles of P of A is equivalent to the category of G linearizations of the trivial line bundle. And the linearization of trivial line bundle on X is driven by GM morphism GM to GM times X to GM, which and the cocyclic condition turns out to be like of this form. Now, in our case, if n is at least 2, there are no non-constant morphisms from an minus 0 to GM. Hence, linearization is determined by a character. And like, we can deduce that the picker group of P of A is Z if n is at least 2. And in case of n is equal to 1, like, it turns out that there are linearizations that are isomorphic, and you get that the picker group is given by Z over AZ. Okay. Now, let us try to define metrics on this. Let us define matrices and line bundles. So if we have a line bundle L over P46, then, like, because we have very good understandings of line bundles of P46 from the last slide, we can prove that L of QP to P46 of QP is a topological line bundle. Now we are going to define, we can, okay, we see that metric, we will give a metric here. like if this is a metric, one can prove that it corresponds to a GM of QP invariant metric on the trivial topological bundle on this space. Of course, when I say GM of QP invariant, like because I have linearization of line bundle, I will get also linearization of topological line bundle. So I have a linearization here, and I say that the metric corresponds to invariant metric. Okay, now if sections for K, I said they are given by invariant sections, and one can see that invariant sections are like 4-6 homogeneous polynomial weighted EK. What does it mean? It means that if you give to X degree 4, and if you give to Y degree 6, then like your polynomial is homogeneous. For example, O of 12, it has sections x3, y squared, or it has also the discriminant. Like, and let me say that these 4-6 homogeneous polynomials of EK satisfy that S tilde of T x is equal to T k S tilde of x. Using this, like we are going to define functions on QP squared minus 0. Like what do? Like at each x, I take a 4-6 homogeneous polynomial that does not vanish at x, and I calculate this. Like this can be shown that it does not depend on the choice of homogeneous polynomial, and like using like what I had written, we can see how it behaves in orbits. Like we get that this is true, and conclusion is that that the metric on OK of QP, P46 of QP, is corresponds to a continuous function QP squared minus 0 to R to positive real numbers, such that the following condition is satisfied. Okay, now we have understood the metrics on line bundles, and let us try to define heights. This stack P46 is proper. I'm not going to say what the proper is. Really, we'll see in a minute what evaluative criterium for properness. But it's not really as one would take evaluative criterion for properness of stacks. Namely, you have rational points of this stack which do not extend to integer points. For example, we have point PP inside P46 of QP. Like it corresponds to morphism GM of QP such that one goes to PP. Like the set of morphisms that are isomorphic to this morphism is given by like T4P, T6P for T inside of GM of QP. Okay, and let us verify that none of these points is that this intersection is empty. Like indeed, if valuation of T is non-negative, then valuation of both things are positive. And if valuation of T is negative, then valuation of both coordinates are negative. We deduce like that none of these points is lying in ZP, hence it cannot define a morphism from GM ZP to A squared minus 0. like it cannot be extended, like the corresponding morphism cannot be extended to the morphism of GM ZP to a square minus 0. In fact, one can see that a rational point of this stack extends to ZP point if and only if the corresponding elliptic curve has semi-stable reduction at like the curve. Like it extends to a ZP point if and only if the reduction at P is semi-stable. We know that every elliptic curve will acquire semi-stable reduction after we increase the field. So like here we can add 6th root of P. Like this is going to be isomorphic to x3 is equal to y squared plus P to 3x plus 1. I have multiplied by P to the power minus 1/6, and I get this. And indeed, like this point, it is a point of P46 of ZP with the square root of 6th root of P. So, like valuative criterion of properness give us that QP point, valuative criterion of properness for stacks gives that the QP point extends to an A point where A is the integral closure of ZP in a finite extension. Okay, now such extent, like if we would take now some elliptic curve over QP, and you do the base change to K, you get EK. And now if you want to extend them to integral points, like we will write spec, okay, let us write spec A to P46. And if you try to define, if you have, for example, line bundle here, like you try to use standard definition to define metric and heights, you have a line bundle, you pull it back, like you get the same metric when you regard E as a point, as a QP point of P46, or when you regard it as a K point of P46. We deduce that this obtained metric is stable for taking extensions. Consequently, the resulting height is going to be stable. So in this way, if we would take such extension, we would produce stable heights. However, we have a problem. The stable heights, they do not satisfy Norco property. If you have an elliptic curve E over Q, you can perform a quadratic twist and you get non-isomorphic elliptic curve E prime to E. Like when I say non-isomorphic, I mean non-isomorphic over Q. Of course, they have the same J invariant, and hence they are isomorphic over C. Hence their stable heights are the same. We have obtained, by this procedure, we can obtain infinitely many elliptic curves, non-isomorphic elliptic curves, such they have the same height. Consequently, we don't have Norco property. Okay. Now let us see how one can resolve this point. We'll take bigger stack, P46 bar, which has more integral points. So this stack is obtained. Firstly, we extend action of GM to whole A square, like the same formula, T times X is equal to T Aj xj. And now let us observe that this stack has enough ZP points. So if you have a rational point, if you have a rational point here, it does extend to here to a rational point, to a ZP point of P46 bar. Why? Because if the corresponding morphism GM of QP to a square QP, like it's given by a, one goes to some couple AB. For v of t big enough, like we will have that t4 a t6b is lying inside of a squared of zp, and hence like you get the morphism gm zp to a squared zp, such that when you take base change to qp, you get something isomorphic to the original point. Like so we have seen that like what we have obtained, that in this stack, like QP points do extend to ZP points. However, this stack like is not proper. Why is it not proper? It's not separated. And to see why is it not separated, like there is a evaluative criterion of separateness for stacks. Like this point admits infinitely many ZP extensions to P46 bar. And evaluative criterion of separateness implies that this is not a separated stack. And let us see why these points, like they are not, when they are regarded as QP points, they represent the same point, but when they are regarded as ZP points, they are not the same. Why? If you would have like consider motion GMZP to a 2ZP, one goes to P3P squared. And if I want that this is isomorphic to one goes to P7, P8, what does it mean? It means that there exists T inside of GM of ZP such that T4 such that I'm going to write T dot P3 P2 is equal to P7 P8. But this means that T4 P3 is equal to P7. Like in other words, this means that this implies that V of t is equal to 1. The valuation, the periodic valuation of t is equal to 1. But if t is belonging to GM of ZP, this implies that valuation is 0. So what we get is that these extensions are not are different points of P4 of Z, P46 of ZP. Okay, and now to define a metric, like first let us observe that the picker group of this stack is Z. Like even when even in the situation when n is equal to 1 and we have stack P of A. For this for the stack P of A without bar, we have calculated that it's Z over AZ. But for PA bar, the picker group is also Z. So of this thing, picker group is Z. Now one can see that line bundle on this stack, like as usual, it will correspond to a grid module, because you want that the sections of O of 12 are like we have seen what we want for sections. You want x3 or y squared. Like you want that degree of these sections is 0. Like you deduce that the O of 12 is the module that has valuation that has graduation such that degree of x is minus 8, the degree of y is minus 6. Okay, and now we define a metric on this bundle, which is unstable. We take a point P46 inside of this. Like I don't define a metric on the whole P46 bar of QP. I define only for this open subsets. It's like resulting, if I would try to do it on all, I would get something degenerate. So let us restrict to this thing. We take a section of the line bundle at this point. And so what we do, we firstly take this infimum for like fixed extension to Z to fixed. So X bar here is a ZP extension. Of X. So for fixed extension, you firstly calculate this model and you take this infimum. And this is standard definition. And now if you want to like, because we have infinitely many, we don't know which one to take, we are simply going to take infimum of all over all extensions to ZP points. Okay. Let us set, we will now calculate this infimum. We set dp46 to be subset of zp squared minus 0 such that either first valuation is less than 4 or the second valuation is less than 6. Okay. Now we call like this set, like we denote by its image in P46 bar of ZP by this P46 ZP prime. And now, like one can see easily that like each QP point of this stack admits unique extension of X in this set. And it turns out that that the norm is precisely what you get if you take this infimum only for this extension. It is not hard to see this. Like if you have some X primitive and you take some other X, which is let's say divisible by more of P, that then like this ideal is going to be smaller. This would mean that the valuation of A must be the bigger. Sorry. The ideal is going to be smaller, and hence valuation of A must be smaller, and consequently the p-adic absolute value of A is bigger. So this infimum is attained for precisely this lift. Okay. Now, if you remember, I said that metrics, they correspond to functions that satisfy, because you are doing we told, I recall, what is it? They correspond to functions from QP squared minus 0 to R bigger than 0, such that this is satisfied. And you can calculate, like for our metric that we have obtained, we can calculate this function. It's going to be precisely this. Okay. Other way how to characterize this function is like you see that it's 1 on the set that we have seen, and that for the others, like you use this formula. If you go t times x, you get this product. Okay. For like if you want to define height, you also need to specify the infinite metric, and we specify it by giving this setting like this. And now we pick any family of functions fp that satisfy the condition that I just written, such that for almost all p, it is we call it toric. In other words, like the one that we have obtained in this one. Then for a rational point of P46, like we pick a lift x tilde, and we define height to be this product. Like one can see easily that this product does not depend on the choice of x tilde. Why? If I had chosen some other lift, for example, t x tilde, then each time t will go out, you're going to get t12. And if you take the product over all t, it's 1. Also, like the product is finite, like this product fp x tilde, because for almost all valuations, you can calculate the valuation of x tilde 1 is 0 for almost all p, and hence it belongs to this set, which requires that valuation is less than 4. Okay, so now we know how to define heights for these stacks. Let us see some examples. When a is equal to 1, 1, 1, 1, and it's belonging to Zn, and of course this quotient, I'm going to write P1, 1. This is precisely the projective space. The height that we defined coincides with the standard height for the metric. I'm going to write the metric. Like for the standard maximum metric, and of course our function fp. Okay, this is metric on O of 1. And for standard, like our function fp is given by maximum in this situation. Okay, like in the case a is 4, 6, then the naive height that we have seen is also an example of the historic height. To see this, like if you take a, b, so that like for their integers, and that's so that for every p, either p4 does not divide a or p6 does not divide b, then ab is belonging to this, because this is precisely what this condition means. And hence, all finite fp are 1, because we have said that fp, this thing, is 1. Hence, like you get that its height is given by the infinite part. Like you get f infinity, and I'm just going to recall that this is precisely, we have seen this on the previous slide. Let us see the following example when n is equal to 1, and we have a integer that is at least 2, then P a of q is precisely this set. Height of point x can be characterized by the unique lift. Okay, maybe I should have said z bigger than 0, such that for each prime p, p power a does not divide x tilde. Like each of this point can be unique, can be lifted to a unique point here, and then this height is precisely x tilde. So if you think what you count, like if you count points of height less than something, you are actually at the same time counting how many integers are there which have no valuation, which are not divisible by p of a for any prime p, that are less than something. And you know that this number is like, it's a classical thing. It's b over z of a. And in several slides, we will see why is this consistent with the prediction of Manin pair. Falting's height is also another example of height that we can obtain this way. Like for places when p is at least when p is not 2 and 3, like the local metric that you get in this procedure is precisely the one in definition of Falting's height. For places 2 and 3, you need to change metric a little bit, because you cannot get this model. But anyway, the metric will be continuous. And for infinite place, our metric is singular. Like one can establish that norm of section y squared is this. And when imaginary part of tau is going to infinity, this behaves as this. Hence, like even though it's singular, it has logarithmic singularity, this Faltings-Height. Okay, we can deduce, like using this, that like singular heights. When I write singular height, I'll assume that logarithmic is singular, that they can be compared with toric heights as follows. Of course, they are smaller than the toric height, but you can compare them as follows. This means that if you manage to prove Northcott property for toric heights, it will also imply for the singular heights. Northcott property for toric heights, like it's true, but it's a non-trivial result. Let us define now measures like P4 on P46 of QP, because we want to like give prediction of Manin pair. Like we set dxp to be hard measure on QP, like normalized with this condition, and let dx infinity be the Lebesgue measure on R. Okay, now we pick a metric. In other words, we pick this function, which is continuous and satisfying this condition. Like this means I give metric on O of 10 this time. One can observe that this measure fp minus 1 dxp dyp is invariant, like this is measured on qp square minus 0. We can see that this measure is invariant. This is not hard to see. Like map from u to t u is given by x. X goes to t4x, y goes to t6y. Like Jacobian of this map is given by t4, t6. And the like absolute value of the determinant of the Jacobian is given by t10 p. Because you have here minus 1, like it's going to be this t power 10 will disappear. And you get that this metric is invariant on this set. Of course, this is not a miracle. The reason is that, in fact, that line bundle of 10 is the anti-canonical bundle for the stack P46. Now we take a hard measure on QP times, and on this space P46 of QP, we define the quotient measure. So we have this measure, like which is invariant for the actional group, and we can define the quotient measure. Recall that quotient measure is the measure that is locally the product measure. Like this. So we have we can this, like we know that this is the quotient. I'm just going to call it. This is precisely QP squared minus 0 divided by QP times. And we were working it as topological space. Now we watch it as topological space and do it with a radon measure. When FP is the toric, we can calculate the measure on the whole set. It is given by this. Okay. Now, like even if you have singular metric, if like corresponding function fp minus 1 is integrable over this set, and p is finite, or like if p is infinite, then you require that fp minus 1 is integrable over this set, you can still define measures. Like this is going to be a radon measure on qp square minus 0, it's going to be invariant for the action. And you can still define quotient measures, and hence, like we define measures even when our metrics are singular. Now let us define the pair constant of stack P46, like the product, of if you take product over all pre primes, because you have a zeta p of 1 in the denominator, like this is not going to converge, and then that's why we divide each time by zeta p of 1 each time. And now we define a pair constant to be product over p prime and times the infinite volume, of course. And now, like, way how to rewrite this, like you write zeta of 10 minus 1, and you take this product where S is the set of primes for which Fp is not toric. Because for toric, you know that you get always zeta p of 1 divided by zeta p of 10. So now we have obtained this zeta of 10. Okay. Let us now formulate the Manin pair conjecture for this stack. Okay, I'm going to now speak a little bit more generality. Let F be a number field. We define a pair constant of this stack, PA of bar, simply by defining it to be constant of this. Why is it logical? Like the complement of this stack inside is given by because like the first one is quotient GM, and it's an open substack of AN divided by GM. The complement is precisely given by a point divided by GM, in other words, BGM. The dimension of this stack is -1, and like hence codimension of this stack, like here, is at least 1, because the dimension of stack is at least 0. Like all stacks that we work, their dimension at least 0. Hence, because codimension is at least 1, it should have, it's logical that it does not have influence on the measure. So like we can define it like this. And then we prove, like for non-singular toric heights coming from the anti-canonical line bundle, that there exists open substack such that the conjecture of pair, Manin pair, is verified. Like why is it verified? Like normally you have here logarithm of b power rank of picker group -1, but we have seen that our picker group is z, so its rank is 1, so we get 0. Normally, the final constant of pair for varieties is defined by taking this constant times a factor that is connected to the location of anti-canonical bundle in the ample cone of the variety. But in the case when the rank of picker group is 1, this factor disappears. Okay. And now let us give some idea of the proof. We are going to precise the open substack on which we count rational points. We are going to count rational points on this substack that we denote by T46. This substack is in fact equivalent to this stack, GMB mu2, and let us see why. Like firstly, we have a morphism GM to GM squared given by T goes to T4 T6. And the action of GM on this stack is precisely the one induced from this homomorphism. Okay, now you have a morphism from GM squared to GM squared. I'm going to write it's given by PR goes to P3 R minus 2 P minus 1 R. Like it's some morphism. the induced morphism, like from here to here, is given by 1t squared. And hence we deduce that if we do quotient gm squared, like I'm going to write like this for 6, like for the induced, the action induced for this morphism is isomorphic to gm squared for gm0, 2, which is precisely gm times gm divided by gm2, and we have seen that this is gm times b mu 2. Okay. Now I'm going to define a sort of adelic space of these stachytors. Like what I do, like I take restricted product T46 of QP, right? I call simply that T46 of QP is QP times 2 divided by QP times 46, where this, like the latest is given by T4, T6, where T is inside of QP times. Like you have this subgroup, and like one can verify that this is precisely this. You have this, and you just need, you're going to get ZP times 2 divided by ZP times 4, 6. Okay, you have this, it's in fact compact subgroup, and you take infinite product such that you, of course, you require the formal store coordinates, like a pth coordinate is lying inside. Now, like the morphism Q to Q P times 2, like it will induce morphism from T46 of Q to T46 of QP, and you can verify easily that that for almost all P, it's indeed going to lie inside of this subgroup. So we have obtained this map. Now we are going to establish that the image of map is closed, discrete, and that the quotient T46 of AQ divided by the image is given by compact group times R. Like to do so, like this is going to be isomorphic to Gm of Q times B mu2 of Q. And I'm going to map this to T46 of AQ. And this is like, in fact, commutative. And here I'm going to get the Gm of AQ times B mu2 of AQ. This, like morphism, hence decomposes as the product morphism, and the image of Gm of Q inside of Gm of AQ, I'll just recall that Gm of AQ divided Gm of Q is compact group times R, like or like you can write like the morphism from GMQ to R bigger than 0 is given by taking the product of absolute values, and like kernel is AQ1, and if you take quotient by GMQ, you get something compact. So you get this, and now you have this part, B mu2 of B mu2 of AQ. I didn't say really what is B mu of AQ, but I guess using this definition, it's not hard to see. Like, and this was studied by this part was studied by Chesnovicius. He proves that the image is discrete, closed, and co-compact, and hence now we have that. So we have obtained already that, like the first two parts, the image is closed and discrete, and now like the quotient is going to be, this is going to be compact, and here we have compact times R. Okay. Let me say one more thing, that I is not necessarily injective. Its kernel is given by, like you can study the kernel of B mu2 Q to B mu AQ. It's in fact given by SHA q mu2, which in our case is trivial, but in general it's not trivial. Now, like we use ideas of Battieri and Schinkel to extend the definition of height to the like a composite group of devices at infinity for this stack. We generalize like we define it like this. It turns out that this is a good definition, and this height is related with this height by a simple thing, by this formula, and moreover, this height is defined on like if this product is defined on T46 of AQ. So what we can do, like we want to, of course, to find the zeta series, height zeta series. We say zeta of s, like it's equal to the sum over rational points of h minus s x. Like this is the same sum of when x is inside of this, like this set. Now here we use a Poisson formula. And now, Poisson formula says that, okay, here I didn't say like it is the Fourier transform over T46 of AQ of the function hs minus 1 with respect to character q. So it's like Fourier transform, and Poisson formula gives us this equality. This group, we have seen it's not that bad. It's compact group times R. If you do the dual, it's going to be discrete group times R. And now it turns out that for a lot of characters, like the transform is trivial, is 0. And so like it's something that we can work with. Like it's we use some analysis due to Chamberlain and Schinkel to prove that the meromorphic extension of zeta series. So you will get a meromorphic extension of zeta series. You'll get pole and meromorphic extension, and you can use the Tauberian result to deduce the final to deduce the theorem. Now let us relate it in last minute or two with counting of torzos, like another example of counting points of stacks. If you have a number field and if you have a finite group, like we will count extensions, the norm of discriminant with respect to the norm of discriminant, like and we have the conjecture of Mal, like which predicts that number of Galois extensions K over F, so the Galois group is G, so the discriminant is less than B, is given with this asymptotics when here A of G and BF of G are explicit invariants of G and of F and G respectively. Now this is proven when J is commutative by Wright, like it's proven by for S3 by Davenport and Hellbrown. It's proven for S4 and S5 by Parkova. There is some other results by Wang, like commutative groups times S3, S4, or S5. There is a counterexample by Kluners. And for us, it is interesting that the Galois extension K over F defines a G torso spec K to spec F. Hence, it defines a rational point of a PG stack. Note that not all points of this stack come from extensions. For example, the one coming from the trivial torsor, like it's going to be the joint union spec K, like like it does not come. It comes from spec K times K, like for order of G times, and it does not come from algebra. But believe that the such rational points do not influence the asymptotic significantly. And now we did some counting for torsors. For example, we did the counting for this group scheme, and we prove that the following asymptotic is satisfied. We use the same method that we have used for the proof of Manin conjecture. And this asymptotic is like the same as in right. Here we get the same exponent, here we get the same exponent. But like the counting is different if mu A is not Z over AZ, that is if a field does not contain all 8 roots of 1. And okay, this is it. Thank you.
Thank you very much. Let's all unmute